transport. First, I'll start out telling you something a bit more about me. What am I sitting in? Any takers?
Well, I'm told you have to have lights, otherwise you can't get you on the
Typhoon, yeah. So it's one of the sort of, I think, great moments, I think, of my career, getting the chance to sit in the cockpit of one of those things after having sweated quite literally for the previous 3 years to get that thing in service, to get the engine working. So it was great. That was Farnborough 2004, actually, and a great opportunity to sit in that aircraft. So and it's actually, if you've ever had the chance to sit in the cockpit, it's quite a scary height. So I had to clamber up this little rickety ladder to get up there. So why am I standing here today? And we talked a little bit about the history of the Templar lecture. This is a little bit about me and why I'm here today. Why did I end up in the industry? And I think it had a lot to do with this airplane, the Lightning. As a young boy, my parents used to take me to Farnborough Air Show, not Farnborough Air Show, down Yeovilton Air Show, and these things just really got me going. You know, the smell of kerosene, the noise, the excitement, fabulous. And it was just brilliant just the other year that I finally got the chance to sit in the cockpit of one. This is one of the few, I think there's only a couple of these left in the world now. It's actually the trainer version of the Lightning, and they've got one at Cranfield. And so they very kindly sorted out for me to sit in the cockpit for a bit. So, and luckily the weather was nice as well. So there you go. So a little bit about my career. First off, down here, I'm going to share, actually, and don't tell anybody else, I've got a bit of a dark secret. I'm not an engineer by training. I'm actually a chemist. I started my life as an engineer, as a chemist, actually at Oxford University. And I ended up doing, so I had first degree in chemistry, PhD in fuel cells. And as we'll see, the strange thing is they've come back to haunt me now because people are starting to talk about fuel cells in airplanes. The other interesting thing was the head of the department at the time was a guy called John Goodenough. And for those of you who watch things like the Nobel Prizes, he's just very recently won the Nobel Prize for chemistry for his work on lithium batteries. So he's almost the father of today's lithium batteries. And I had a great privilege to actually be in a meeting with him once a month for a period of time whilst he was the head of the department there. And of course, lithium batteries now are finding their way these days into little aircraft, as we'll see. So after that, my first job, I went to work for BP Research Centre at Sunbury, not a million miles from here. Used to be nicknamed the University of Sunbury-on-Thames, and it very much was like that. I went to work there on oil processing. So yeah, another form of energy conversion. I was working on cat cracking, which for those of you who know these things, it's the big chemical processing unit in an oil refinery that converts some of the elements of crude oil into gasoline. So it's a huge money-making machine, and in most refineries. So we were looking at the technology that was going into those things at the time. But then I finally got my moment in aerospace and moved to Rolls-Royce in 1990 at Bristol into the combustion department. I think they thought chemists might be vaguely useful, thinking about burning things, molecules and all the rest of it. So I got a job there at Rolls-Royce in Bristol in combustion research. And I think, I always thought as part of the bargain, they trained me on the job to be an engineer. So I've always been a bit of a seat of the pants engineer and a bit of a pragmatist. I like sort of fiddling with things in my garage and all that sort of stuff. So I see myself as quite a practical engineer and always challenging the real engineers to explain to me how things work. But these are some of the engines I worked on in the defence business in Rolls-Royce. The Adore, and spent a little bit of time there trying to make the engine last a bit longer, to put up with the abuse that the US Navy were putting it to in the T-45 trainer. And then spent some time working on the RB199, which is the engine on the Tornado. And it's a really sort of sad day, actually, that a few of us made it down the end of the runway at Cranfield the other year when that sort of flight of 4 Tornadoes was going around the country. So there was definitely a tear in my eye at that point. And then I spent 3 years actually out in Germany running the engine program for the Eurofighter, the EJ200, and that's really my baby, I would say. And it's an incredible machine, thrust-to-weight ratio of about 10 to 1. It's actually a very simple engine compared to its predecessor, and I'm pleased to say it's doing incredibly well in service. And the measure of that is I bump into some of my old Eurojet colleagues every now and again, and some people who are working for Eurojet who don't know me or vaguely heard about me. And once they hear my name, they'll say, oh, you're the guy. And I say, what's that then? They say, well, you really messed up on that engine. Why is that? Well, you made it too reliable. We're not making enough money. So, you can't keep everybody happy. But I go and talk to pilots, and I ask them, well, what do you think of the engine? And they say, it's fabulous. I don't have to think about it. They said, we don't think about it because it just works. So, really pleased with what the team achieved there. And it was a huge team effort over many years. And, I was lucky to be there really at the peak of the program to just sort of get it home. After that, came back from Germany, went to Derby, the great centre of Rolls-Royce, of course. Huge, it takes over a vast part of Derby actually these days. And I worked on everything actually but jet engines. And we worked on superconductors, nuclear power, underwater marine current turbines. So I spent a period of time heading up their Blue Skies research lab. So it was quite fascinating. And there was a really big push by Rolls-Royce at the time to get into all forms of green energy. Then, as Jonathan mentioned, I spent some time actually running control systems for civil aerospace. And you can see a couple of engines that the team there were working on. I had about 700 engineers working for me at the time. So that's the BR725, which is found at home at the time on a Gulfstream business jet, and the Trent 1000, which is, as many of you know, the engine on the Boeing 787. So we had I remember a huge team of engineers at the time working on the Trent 1000 to get the control system certified. And for those of you who are familiar with control systems, we were always the tail end Charlies. The sort of final lines of software, and the validation program was always the last bit of the program to get finished. So we were always in trouble. And then finally, my last years in Rolls-Royce, I spent about 4 years running the global aerospace technology program for Rolls-Royce. It's a massive program. At the time, it was about £200 million a year, spread across the UK, spread across Germany and the United States. So that was a great time, and worked across the world, set up a university research centre in Korea. Spent far too much time in karaoke bars in Korea, even to the extent I got offered a job as a guitar player once in a Korean karaoke bar. But that's another story. And then I had certainly spent quite a lot of time working with government and other industry colleagues around the inception of the Aerospace Technology Institute. And for a number of years, industry had been almost pleading with government to say, well, look, compared to other countries, the UK is at quite a major disadvantage. We don't have, the government has not accepted a strategy investing in aerospace technology, and hadn't done, for 20, 30 years. Increasing signs that industry was starting to drift to other places. Eventually, the arguments won through, and industry persuaded government to put in a very significant amount of money into aerospace technology. And at the same time, it was announced that we would form the Aerospace Technology Institute. And I'll tell you a little about it, what that is in a moment. But that gave me, and I was offered the opportunity to take on the role that I'm currently doing today. So left Rolls-Royce, joined this almost a startup at the time. I was one of the first 10 employees. And it's been a tremendous journey, a tremendous experience, and met many, many new people across the country in aerospace. So going from being really sort of focused on engines most of my career to start to learn about the whole aircraft and all the systems that go on it and so on. So it's been a great privilege and a great experience. And I'll tell you a bit more about that now. So a bit about the ATI. So our mission as it is today is to lead technology in air transport in the UK. We set up in 2014, September 2014, and that's when I joined. We're actually an independent company, not-for-profit company, jointly funded by government and industry. So we're an odd sort of entity, really. And we've been set up to provide leadership for the UK's aerospace technology community. We define the UK's national aerospace technology strategy, and we lead the development of a research and technology portfolio will be worth 3.9 billion by the time we get to the end of 2026. You can't imagine really how large now that program has grown to. I'll tell you a little bit more about that in a minute, but that's a vast amount of money compared to what the industry used to get. And, that is making, I'd say a huge difference. Every day we talk to people and they talk about the difference the ATI makes because much of the industry these days is maybe headquartered outside of the UK. And it's a really powerful message to give to people that, yes, the UK is a great place to do research in aerospace technology. And we're always seeking new ways to stimulate technological innovation and create UK advantage. Oh, I was doing some really flash things with PowerPoint. Interestingly, it's a little tilt rotor picture there. And I was down at Leonardo in Italy last week. The weather was much better than it is here, I can tell you. And we got a tour around the AW609, which is the Leonardo tilt rotor. It was quite a fascinating thing to do that. And they've got about 3 prototype aircraft. This one was in a sort of, the engines were out of it and some of the panels were off, which was actually for an engineer really good because you could see how some of the systems worked and so on. We were shown around by the chief engineer, so and he was really good at answering our questions. So it was a great experience, and I, that's the thing about my job. It's brilliant because I get to do all sorts of fun things like that. So some of the sort of visible examples of our output. So we've got a small technology team in the ATI who work for me, and also in conjunction with other colleagues in the ATI. We've been working very hard to put together a whole portfolio of strategic thinking, you'd say, that we publish. You're free to download all of these documents off of our website. So if you're interested to kind of follow up a bit on this, please help yourself and download all of these insight documents, which are detailed looks at different areas of technology. Usually our sort of crowning achievement is when we issue our strategy document, and over here, the one on the right-hand side, Accelerating Ambition, is our latest version of our strategy. We published this in November last year at our second conference. So it was a great occasion, and it's been very well received. And again, you can download a copy of that I'm going to spend some time telling you about, really, from our website. So at the top level of the strategy, what are the key messages? And it's very simple. Actually, all of our program is about one or more of these things: sustainability, mobility, and competitiveness. So we're going to have a little look at each of those in turn, and perhaps give you a little bit more of the thinking behind each of those. Some charts here. I don't know if, hopefully, well, I'll explain them because some of you near the back may not be able to see these too well. So this chart here, you can see a steadily upward moving line, time across the bottom, and passengers transported. And as you can see, we're on an exponential growth curve in terms of the commercial aerospace industry. So the number of passengers, number of flights, number of aircraft, however you want to measure it, is increasing at something like 4.5% a year, year on year. And it doesn't matter, it seems up to now, whether we have Gulf Wars, the oil shock back in the end of the 1970s, 9/11, global financial crises, they're all just little blips on that ever increasing curve. So what are the sorts of factors growing that demand for air transport? Well, the real cost per mile of flying has been coming down over time. But also things have been happening in the global, if you like, the global economic picture. You've had the economic growth of countries like China and India, and the effect of falling air ticket prices and the growth of those economies is driving, largely responsible now, particularly for the growth over the last few years, and will continue to drive a massive demand for new aircraft. And if you talk to, we talked to Boeing a little while ago, and they said, well, and this was before they hit a few problems, but they reckoned they'd sold out their production for at least the next 10 years. So we know that that line is going to continue to go up for at least the next 10 years because the aircraft have already been sold. And the story is the same for Airbus. So obviously you start to think, gosh, this rapid pace of growth, more flights. Yes, one of the byproducts of that is that aircraft do create CO2 when you fly them. That's the best way we found at the moment of powering aircraft, is fueling them with kerosene, burning it in jet engines or turboprops, and flying around. So yes, we're steadily producing more carbon dioxide, but at the same time, we've done a pretty good job from the engineering point of view on improving the fuel efficiency of new aircraft. So here you can see the curve going steadily down over the years. The most recent aircraft on there, I think, is the A350 and Boeing 787 at the bottom. Very highly efficient aircraft compared to when the jet age started. And we're continuing to improve the efficiency of new aircraft by about 1.5% a year. But the problem is, if you remember the other number I gave you, 4.5% a year growth of aviation, we aren't quite keeping pace with that growth in the market. So it's a big challenge. What are we going to do about it? This was a graph published by a group called ATAG. It's a kind of global grouping of the aerospace industry, and shows what we might do. So if we do nothing and we just let the industry grow at 4.5%, the red dotted line at the top, that's what we'll get in terms of CO2 emissions. They'll continue to grow at 4.5% a year. If then we start to bring in new technology, we can mitigate some of that, but it won't be quite enough. So what are some of the other things we might do? We might take economic measures. We could put carbon trading in place, so somehow tax people, if you like, for the amount of carbon they produce. That might incentivize if you like, the acceleration of take-up of new, much more efficient aircraft. The other thing, and I think one of the single biggest things that we can do, is start to develop alternative sorts of fuels. Almost as a stopgap, people are looking at biofuels, but at the moment aerospace is competing with the automotive industry for biofuels, and they're very expensive compared with kerosene. But that might be the price actually of reducing CO2 emissions over time. The other thing people are looking at long term is, can we make so-called e-fuels? Can we suck carbon dioxide out of the atmosphere, react it with hydrogen that we make using electrolysis, using lots of green energy, and synthesize kerosene? So you end up with almost a closed carbon loop now to fuel aircraft with. Sometime off in the future, but I think that is a really good long-term prospect. And as we'll go on to see a little bit more on propulsion, for longer range flight, kerosene or kerosene-like fuels are probably will remain the best solution going out into the future. And there's a lot of reasons for that, and we'll talk about that a bit later. Okay, one of the things I was involved with, and still on the sustainability theme, was setting the European technology targets for aerospace. So I was a member of the so-called ACARI grouping. Some of you may have heard of that. It's a big European-wide committee. All of the major aerospace companies in Europe belong to it. And back in 2011, we all got together at the request of one of the European commissioners to set some really challenging targets on the environment for aerospace. So we said, relative to say, and it was a 1990 baseline, we were going to reduce CO2 emissions by 75%, NOx by 90%, noise by 65%, reduce the accident rate by 80%, getting on towards an order of magnitude, and cut the certification cost. And these indeed have proven to be very, very challenging targets. I'm pleased to say we've probably got the best chance at the moment of getting towards the emissions target for CO2 and NOx. The 75% still doesn't get us quite far enough, really. Because now the government is setting really ambitious target of zero net carbon. So how do we get there? So that, there's another challenge to think about on top of that. But we're making, I think, pretty good progress, as we'll see. So let's think a little bit more about sustainability. What can you do about it? Well, actually, if you look at the media, the big thing the media are talking about now is electric. Can we just go electric? Not as easy as the media think it is. Actually, in reality, and I'm sure you'll realize this, there's no silver bullet to sustainability. You need to attack it from a number of different axes. Obviously, the air vehicles themselves, can you make them much more fuel efficient than they are today? Yes, you can. There's still a long way to go, even though we've spent over 70 years working on jet-powered aircraft. There's a long way we can go. Flight operations, we could fly aircraft much more efficiently than we do today. Today, our air traffic control system is based on a system that's decades old. It's driven by people looking at radar screens and so on. There must be a lot more that we can do to enable aircraft to fly the most efficient route that they can from A to B. Some work that's been done recently, and both Boeing and Airbus have been looking at this, is what's termed as formation flying. This has been known about for quite a long time. You see big flocks of birds flying around. Certainly when they do it long distance, they'll fly in formation because they get the birds following the lead bird get awake a wake benefit. They slipstream. It's just the same for aircraft. Interesting, you don't have to fly that close to get a beneficial effect. And actually, even if you're about 1 kilometre behind an aircraft, you get an effect. So obviously, there's some technology to be done there. How do you do that reproducibly? You need some position keeping, to do that in an automated way. How do you share the financial benefits? So, there'll be, if you're the plane in front, you're burning more fuel than the ones behind. If you're different airlines, how do you share the benefits? So, there's a little bit of thinking left to be done there. But the benefit might be as much as 10%, and 10% from being able to fly more directly from A to B, plus 10% for formation flying. So there's a lot to come just from that. Manufacturing, the impact of manufacturing is tiny on global CO2 in comparison with flying, but it's still important. Every little counts, and so much of the manufacturing research that we fund through the ATI is going into much more efficient, more sustainable manufacturing techniques and technologies. Ground operations, many airports now are committing to go carbon free by sometime in the next decade. Heathrow has made commitments on going zero net carbon, not in terms of the aircraft, but all of the operations and on the ground. And if you think about that, there's loads of trucks and their heating and lighting and all those sorts of things. So again, that helps. We aren't very good as an industry about thinking about the full life sustainability of our products. And this is going to be a growing issue as we go out into the future. So aircraft now are transitioning from metallic structures through to composites. One day, do we really want to see huge, great fleets of carbon-based aircraft out in a desert somewhere in the United States? Probably not. So what are we going to do with aircraft in the future? So composites are, whilst offering a lot of benefits in creating lighter aircraft, more fuel-efficient aircraft, there's a real problem there in terms of closing the loop on the life cycle and recycling them. And we've already started to talk on how you power aircraft, how you fuel them. So we talked about alternative low-carbon kerosene-like fuels. Yep, you could power an aircraft by batteries, or you could power an aircraft with hydrogen or natural gas or something like that. So there are alternatives that don't necessarily generate as much carbon, but they've got disadvantage. Whilst they produce less carbon, they have other disadvantages. So some advantages, some disadvantages. But at the end of the day, no silver bullet, I'm afraid. We've got to work on all of those things. So that's the sort of message that we're giving through to government. And ATI these days is in quite a sort of, I'd say, a very influential position with government. We advise government very closely, as they don't have internal technical specialists like they used to. ATI these days, it's falling to us to make sensible technical advice into government, which is a very, I guess, a very privileged position to be in. It's a very responsible position to be in, and so we tend to think, spend a lot of time thinking through what advice we're going to give. Okay, so a little bit about, remember, sustainability. The other one was mobility. So can you use the air to unblock some of our transport system? At the moment, we're stuck in, largely speaking, to get around the country in two dimensions. We're using the roads, we're using railways. They're already very, very crowded. If you look to the UK today, traffic jams alone cost the UK something like about £10 billion a year in lost productivity, and that's just traffic jams. Today, you know, many of us spend far too much of our lives actually sat in traffic jams. I know I do, or sat on trains, and people are taking longer and longer to travel to work. Your average commute time into London now is 70 minutes. I know I go into London twice a week. It takes me 2 hours. It's far too much time out of my life. So how do we unlock that transport problem? The air is certainly an option, but how do we do that in a sustainable way? So if we create new vehicles that are optimized around doing shorter ranges around cities and out in the countrysides, surely they've got to be zero net carbon impact from the start. Why would we add to the problem we've already got? So those vehicles, almost by definition, have got to be electrically powered. So we'll talk a little bit about how we might do that. The infrastructure supporting those vehicles, it will be much larger than the air transport infrastructure we have today to make an impact on the domestic transport situation. That has to be zero net carbon. So airports are going in the right direction, but we'd need a lot more airfields or airports to support a big expansion on the use of the air. How do we control many more vehicles in the air at one time than we do today? So today, across the UK, NATS handle about, I think the maximum they've handled so far is about 8,000 flights in a day. Imagine growing that by orders of magnitude, and particularly if you brought drones into the equation, it's that problem is probably the biggest one in terms of using air on a large scale for mobility. So I almost think that one of the key elements to this problem is unlocking the air transport system, the air transport management system. And then, of course, all these bits and pieces giving rise to new business models. In fact, people now are talking about using the air. You know, if you imagine drones and what sort of things they might do, deliver parcels, people are already sort of demonstrating they might be able to do that. People are already using drones inside of factories. You've heard of a company called Ocado. They're starting to use drones inside of their massive delivery centres that they have. And so they're finding, by the day, all sorts of new uses. People would like to be able to fly drones beyond the visual range from the operator. And so the future ATM system must be able to accommodate that. And you know, it's a complex problem. Eventually, we could be using drones to build buildings. Why not? You know, so you could almost let your imagination run wild on that one. But a lot depends on how you manage those air vehicles in the air and their interactions with buildings, with other air vehicles, and so on. So a very complex problem to solve. One of the things the ATI did was to pull a big group of industry together and academia to form a program that's known today as Future Flight. And so that's taken off, there's a bit of a pun, in its own right, and was successful in gaining government funding. So that program is now gathering pace, and maybe some of you know people who are already involved in that. And then lastly, competitiveness and ATI and the funding we put into research today is a key part of the overall industry support network across the country. Includes our UK ecosystem, academia, manufacturing research centres, other industry support mechanisms. We, ATI and other bodies, help industry to connect to customers and form collaborative relationships. There's another group here at the centre of all of this, World Aerospace Growth Partnership. This is a senior level industry committee, and effectively the ATI is an offspring of the Aerospace Growth Partnership. And they meet occasionally with government ministers and so on. I think they've got a meeting with Boris coming up soon, so we'll keenly await the outcome of that one. Just to sort of summarize that, if you remember the three key elements of the strategy: sustainability, mobility, and competitiveness, and you can trace those through everything, all of the projects that we're funding. So if we took that air transport view down a bit further, most of our projects that we have at the moment are funding work on sustainable air vehicles, propulsion systems, the complex systems that go on aircraft, and the structures of aircraft. So let's take a little look at each of those in turn. So what are our priorities then on sustainable air vehicles? So firstly, we've been sort of holding this thing right at the top as a critical element for the industry. It's actually retaining and growing whole aircraft design and analysis capability. I think without that, you lose the ability to understand what technology you need in the future for aircraft. And so one of the things that we've done in the ATI is to create our own small team and a modest capability, although it's very capable, to understand the fundamental design of aircraft and how they perform and so on. And we're using that capability to understand the benefits of new technology at a whole aircraft level. And we're also trying to use that as a bit of a catalyst to help that capability to sustain itself and grow more in the future in the UK. Because at the moment, we're not making whole commercial aircraft to any extent in the UK. We're still thankfully doing military aircraft through BAE Systems and rotary wing vehicles down at Leonardo's. But in terms of large commercial aircraft, we're not making those. We make the components, yes, the wings, the engines and so on, but we don't build the whole aircraft at the moment. So we do need to ensure we find a way to keep that capability going. We want to ensure that we're a key player in the delivery of future sustainable commercial aircraft. And this means being ambitious in launching aircraft level demonstrators or being part of aircraft level demonstrator programs globally. So a big question here is obviously after Brexit, how do we do that in Europe? And that's a challenge that we're taking on. We're continuing to maintain relationships across into Europe after Brexit for sure, because a lot of the industry, our UK industry, depends on that trade with Europe and interactions being part of European commercial projects, particularly with Airbus and the other large European-based aerospace companies. So that's what that's all about. And then leading the way forward for new sustainable air vehicles for what we call urban and regional markets. So this might be air taxis or aircraft that have shorter ranges that are effectively zero net carbon. Here's a little picture of one. This has actually been produced by a company called Vertical Aerospace in Bristol, just down the road from Jonathan. And a very interesting little company. They've got about 100 people working for them now. They've been flying their second, they call it their sort of almost like phase 2 demonstrator, which is a multi-copter vertical takeoff vehicle. They're currently working on their next prototype. They said they can't quite get it ready for Farnborough, but it will be ready soon afterwards. So they're making really impressive progress, and this is all electrically powered. It's battery powered, and they're still looking at how they're going to power their next one. It's probably a hybrid aircraft of some type. But there's some really exciting things happening in the UK today around some of these novel sorts of air vehicles. So what are we going to do about aircraft fuel efficiency? Well, a couple of real main things. If we take propulsion aside, because we're going to cover that in a minute, you can make aircraft aerodynamically more efficient, and you can make them lighter. And Jonathan knows all about trying to make aircraft lighter. Obviously, ways that people have been looking at over the last few years is making them increasingly out of composites. And if we look at, say, the A350 today and the Boeing 787, those are substantially composite aircraft. And composite wings, because of the way you can carry loads and so on, and Jonathan can explain this better than I can, but enables much higher aspect ratio wings, so much thinner, longer wings. And here's a prime example. That's the latest version of the Boeing 777X. And you can see the wings here are such high aspect ratio now, and the diameter has got so large, they're having to fold the wings up on the ground to enable it to maneuver around. And so it's had its first flight only just recently. So really impressive looking aircraft. And you can find some pictures on the internet that compare the before and after, and the new version in comparison with the old one, and how much bigger diameter the wings are. And a great sort of part of this story, and linking locally to capability here, is that Boeing do quite a lot of their fundamental aerodynamic testing on the wind tunnel at Farnborough. And talking with their aerodynamic specialists, they say there's only two tunnels in the world that are good enough to do the sort of testing they want to do. One is at Farnborough. The other one's in France, and they said, well, they don't particularly want to go there. So they prefer to come to Farnborough. And ATI have been actually putting some funding into the Farnborough facilities to update and modernise the capability there. So hopefully that capability will be there for decades to come. We'll be there to try and make sure that does happen. So yeah, we talked about the composite wings, higher aspect ratios. That's kind of, I call it passive aerodynamics. The next step is to go to more active control of aerodynamics, and people are looking at different ways to do that. Here's a picture of the Airbus Blade demonstrator. This came out of the European Clean Sky program. And here they were doing research on laminar flow control, so actively sucking air into the wings to try and keep the boundary layer attached and to reduce the drag. I've still not heard the final analysis of the results coming out of there, but obviously people are optimistic on that. One of the big challenges with these laminar flow systems, if they've got thousands of small holes sucking air through them, is that they've got a tendency to get blocked. Things like flies and dirt and whatever can block those holes. So I think it's a challenge still to be overcome, and I think the jury's still out as to whether or not that will be a viable system for the future. Other things that people are looking at, and this connects more with so-called hybrid propulsion, or a mixture of electric and jet engine propulsion, is using the power generating capability of jet engines to power an additional propulsion system. And in this concept here, there's a fan, electrically powered fan system sat in the back of the fuselage that is sucking away some of the slower moving boundary layer flow around the fuselage. And there's many people thinking now that might be a potential solution for larger aircraft in the future. Alternatively, we could go to different architectures altogether, and the most aerodynamically efficient is a so-called blended wing body. And this picture just appeared in the press actually a couple of weeks ago. Turns out that Airbus have been doing a fair amount of work, perhaps not surprisingly, on blended wing body architectures. And they claim this can give, this sort of configuration can give about 20% better fuel efficiency than a conventional tube and wing. There are some issues with one of the issues with it, say in comparison with the tube and wing, is you find it more difficult to make a family of aircraft out of these. With the tube and wing, you can just put plugs in the fuselage and stretch it and create a family of aircraft. Much more difficult to do it with that. So you can combine this idea with that idea. So active control of aerodynamics with a blended wing body. So here you can see the engines sit over the top of the fuselage. They're sucking in actually boundary layer flow over the top as well as propelling. So they're also actively enhancing the aerodynamics, the airflow over the top of the wings. This is an even more extreme example up at the top. It's the so-called silent aircraft concept produced by Cambridge University a few years ago. But there's a real urgency, and particularly around these ideas for smaller, I call it urban aviation aircraft. That number's, and I did this chart actually a little while ago, about 18 months ago. So today there's perhaps over 200 electric aircraft projects going worldwide. An astonishing number, and it's almost a new era of aviation that's starting up. Now, many of these are going to fail just for a number of reasons. Financially, they'll run out of money. They've underestimated probably how much work it's going to take to certify one of these things. They may not be able to find enough engineers, and that's a problem, I think, for all of us these days. Can we find enough of the right people to make that work? But there's some big programs going globally. Uber, the taxi company, well, they don't actually own any taxis, but they deliver a taxi service, have launched a couple of years ago a big initiative to develop or catalyze this industry, for, if you like, for air taxis. Japan have got a very big program going there. The UK now, we're between the ATI and the Future Flight Programme, we're also trying to accelerate that thinking and work in the UK. And a lot of it, this depends on propulsion in the future. And almost all of the improvements in large commercial aircraft over the last 30 years has come from the propulsion system. And Tom Enders, who was the previous CEO of Airbus, admitted to that. Of course, me being an engine person, that's actually really good news to hear that. And I think propulsion will continue to be, if you like, one of the main angles that we're looking at to improve the fuel efficiency of aircraft. And there's a lot to come. ATI, we're looking at three main things. Ultra-high bypass ratio turbofans, so the UHBR, we'll talk about those a bit. Hybrid gas turbine systems, so that's combining the generating capability of gas turbines with some of the flexibility that electric propulsion gives you. And then lastly, all electric systems such as battery or fuel cell propulsion options. So let's talk about the UHBR and a quick 101 of jet engines. So this is where we are today. So this is the most efficient engine, as Rolls-Royce say, currently in commercial service, the Rolls-Royce Trent XWB 97K engine. That's a catchy name. And that's running at a bypass ratio of 10-1. And bypass ratio for the future engines is one of the sort of most important numbers to keep your eyes on. That number tells you roughly how much air goes through the fan in comparison to how much air goes through the core of the engine. Just a sort of simple explanation of the bypass engine is that it's basically two parts. The fan on the front, this is the bit that you always see when you look up the front of an engine with the nose on to the aircraft. Behind sits this narrower part of the engine. It's called the core. In the core, this is where you do most of the compression of air, burn the fuel, expand the hot gas at the other end to generate the power to drive the fan. The fan provides most of the thrust. And so for the sorts of flight regimes that commercial aircraft today fly in, this is the most efficient way of propelling an aircraft or large commercial aircraft around at the sort of speeds that they want to operate at. Hugely complex product, 20,000 parts, and a very expensive product as well to produce. Advanced materials and so on, huge amounts of technology. So how are we going to get to higher fuel efficiency? This is already a very efficient machine. We're going to work on two things. The fan system. We'd like to make it lighter weight. So current generation is titanium casing, titanium fan blades. Ultimately, we want to go for these nice, pretty coloured ones, which are composite. And so certainly for very large fans, composite blades start to win out because if you've got composite blades, you can actually put a composite casing on as well. So it ends up being a much lightweight system for larger scale fans, the sort of thing we're contemplating now. You also need to work, as well as working on the fan, make it much higher diameter, increasing the bypass ratio to propel yourself more efficiently. You want to get more power per unit mass out the core to overall reduce the mass of the engine and drive you more efficiently. So you're trying to drive the core to a higher pressure and a higher temperature. And so together with Rolls-Royce, we've been providing funding into what's called the Rolls-Royce Advance concept engine. And that engine demonstrator is run. And that's provided the technology for a new generation of gas turbine cores, highly fuel efficient. It's got a very different architecture once you start looking at it in detail on the compression system. And that's the key to it. And that's the key to really what I call the ultimate jet engine, which is this thing. Rolls-Royce call it the UltraFan. It's an ultra-high bypass ratio turbofan. So what does that term mean? It means the bypass ratio is above 15:1. So those engines will, if they aren't big enough already, they will appear even bigger in relation to the scale of the aircraft. And so, these engines will, I think, grow to dominate air transport in the years to come. In fact, a company called Pratt & Whitney already have a geared turbofan running. That's only running at about a bypass ratio of 12:1. So certainly not as ambitious as this, but it's a step on the way. And it's already been pretty well proven in service. And up here you can see just a cutaway, perhaps a better cutaway of that engine. Here you can see it's actually got a couple of rotating stages of compressor, two turbines that are linked to those compressors. And they actually connect to the fan through a very large gearbox. So why is that? And it's because basically turbines like to run at high speed. You get better performance out of a fan if you're going to run it at slow speed. So you need to disconnect, if you like, mechanically, apart from through a gearbox, so you can get that sort of different ratio, speed ratio from the fan and the turbine. So we've also got to design and develop a very highly power dense gearbox, about 50 megawatts through something a meter in diameter and half a meter deep. Pretty impressive machine. And if you think about it, if you're putting 50 megawatts through, if that's even 1% inefficient, how much heat you've got to lose out of your oil system, because you're basically cooling the gearbox with oil. So a very formidable challenge that you have to have a very, very highly efficient gearbox as well. So what will that give you in terms of emissions performance? So you remember we talked about today's Trent engines. They sit about here. So relative to, let's say, 80s technology, which is the Trent 800. So we're telling, you remember the Akari story. So relative to 1990, we're somewhere between 10 and 15% better on fuel efficiency over that time. And here's what the Advance core and ultimately UltraFan will give you, something like about 25% better than the Trent 800 was. That's the engine, Rolls-Royce engine that was on the first versions of the 777. Boeing 777. We still have got about another 5% to bridge, so a bit more thinking to do. But there's a bit of time before 2050. So, we can certainly start to see a way on the engine side to reach the ACARI targets. But in terms of getting to net zero carbon, this is where we need things like alternative fuels to take carbon out of the equation. So electric propulsion, what's going on at the moment? Actually, I'm pleased to say there's a lot of ambition in the UK now. In fact, we've got at least 4 live projects running in the UK. The biggest one is this thing. It's called the EFAN-X. It's a joint project between Airbus and Rolls-Royce. And it's developing what's called a hybrid propulsion system. It's a mix between electric and gas turbine. That fuselage on this aircraft, and it's a BA 146 that's being converted. That fuselage is virtually full. It's got a turbo generator in it, a big power electronics system and a battery. All that to power that little fan that sat out on the wing. So the challenge is shrinking all of that lot into something that big. So a little way to go. This thing is also a hybrid aircraft. Interesting project. It's based on a Britten-Norman Islander airframe, and Cranfield Aerospace Solutions, a little company, they're an offspring of Cranfield University, are looking at electrifying that, so fitting a form of hybrid propulsion to enable this aircraft to fly around the islands in Scotland. And the interesting thing is that they originally thought, we can just use batteries. The problem with batteries is per kilogram, you can't carry much energy in comparison with kerosene you might use on a conventional aircraft. In fact, you're about 2 orders of magnitude away in terms of energy density. So that's why the day where we might see large aircraft flying longer ranges on battery it's a very, very long way. So in fact, we may never even get there with battery power density. So they realized that actually the divert case for this aircraft, so if the weather comes in bad over the islands in Scotland, you have to divert back to the mainland. So you actually have to have endurance to take you hundreds of miles rather than just tens of miles between the local islands. So they're having to go to a hybrid system. So that's a hybrid. You can also power aircraft by batteries, we were talking about. They will only fly for short distances. This is a really interesting project that ATI are funding with Rolls-Royce, is to make an all-electric high-speed aircraft. They're making an attempt on the world speed record for electric-powered aircraft. This project is based at Staverton Airport in Gloucester. Interesting project. It's due to fly fairly soon. They're hoping to fly it at Farnborough. So if you're at Farnborough, you may well see it fly in. And another interesting project we're involved with, this is with a company that we've worked with. They've come over from the United States, is to build an aircraft with a hydrogen fuel cell powered system. Now, the advantage with hydrogen is it's many more times energy dense than batteries. So energy per unit kilogram. In fact, it's higher than kerosene. The problem is it's volumetric density. So even if I had liquid hydrogen, I'd need fuel tanks 4 or 5 times the size of a kerosene tank. So that would lead to some pretty fundamental issues in designing aircraft to accommodate that. So at the moment, for long-range aircraft, a kerosene-like fuel will be the preferred option for a long time to come. For shorter range, very, very short range aircraft, probably a battery, but you can only get a very short flight out of it. For somewhere in between, perhaps hydrogen might be the solution, and connected to a fuel cell, which is a very efficient way of converting the energy, chemical energy in hydrogen, to electrical power. Systems, and I'll race through the rest of the viewforms because I'm getting in between you and food. So 3 big things on systems we're trying to do. Firstly, optimizing the next generation of systems and equipment. Here you can see a picture of a future cockpit concept. So we've got a big project going on at the moment between BAE Systems and GE in Cheltenham on future cockpit systems, including force feedback joysticks and virtual reality and so on. Connectivity is a big thing in the future. How do we get much higher bandwidths in terms of transmitting data on the aircraft and from the aircraft to the ground? Might be through satellites or directly through mobile phone links and so on. So we're working with that, the communications industry, if you like, and both companies that are looking at communications on board, but now work with companies such as Inmarsat to understand how we might transform connectivity in the future. And the other key, I think, in the future of flight, particularly if we're going to vastly expand the air transport system, is the use of autonomy. And particularly if you've got aircraft that take off vertically and land vertically in the future. I had as usual, any of you who've had a go at trying to fly a helicopter, I had a go on a simulator down in Italy last week, and as usual, I couldn't get very far in the helicopter. It just sort of suddenly flipped over. Couldn't quite work out. You need about sort of amazing levels of coordination to fly these things. So you can't contemplate letting the average person handle one of these things. It's got to be substantially autonomous, really, in the future. So I think that'll be a key issue for aerospace in the future. Structures. UK, we are one of the world's leading places for wing manufacture, both the assembly and the manufacture of large composite structures. We definitely want to make sure we stay a leading nation there, and there's a huge program called Wing of Tomorrow, centered on the next generation of Airbus complex of composite wings that's taking place right now. In the future, we might be having wings that can change shape, flexing wings and so on. How do we make that happen? And then we've got to come on a long way on assembling these very large structures in the future. Can we substantially automate that much more than is done today? And not forgetting, going right through everything, we also need to bring through what we call high-value design, the capability to design and integrate complex systems. We need to work on the materials coming through, manufacturing and assembly, and how do we support these products in a more efficient way through their lives. So from our very sort of small beginnings, the ATI now have grown to do a whole range of things, and this is across a team of only just about 30 people. Of course, we work with a lot of groups that effectively magnify that effort, but even so, we do cover a remarkably large ground, right from the large strategic programs we just talked about, right down to through to supporting small and medium companies through the NATEP program and collaborative R&D projects. We're running big events such as our conference last year. We even have just started up what's called an accelerator program to help new companies come into being. So a whole range of activities. Here's an idea of the scale. So today we've got now £2.6 billion worth of projects on our books, and that's in just about a 5.5 year time span. We've built that portfolio. Now over 300 projects, about 180 of them are live, and the economic calculations we've done show that will support at least 66,000 UK jobs in the future. By the time we hit our budget of 3.9 billion, that'll secure at least 90,000 jobs. So making a real impact on the future of aerospace, and just out of a very, very small team that try and pull all of that together. We're looking now at the next phase of ATI because our budget at the moment runs to 2026. So we're working with government at the moment to see if we can extend that horizon out to 2036. I'll be certainly retired by then, hopefully. And and that will continue to support the industry out into the future. Pulls a lot of companies in, over 300 different organisations that are part of that. Over 200 SMEs who are direct partners. There's a lot more who are suppliers into these programs. And largely speaking, most of this that we do are very big programs. So the average size of grant in the program is $1.5 million, which means the program size is about 9 million. So that's almost the smallest unit for many of our projects that we do. Some of our projects are 30, 40 million pounds in scale. So they're very, very big projects. And we've also had a big impact on the national infrastructure for aerospace. So all the different little boxes here are standard pieces, multi-million investments in large experimental infrastructure. And we talked a bit about the investment we've made locally at Farnborough. And just you can eyeball the pictures here, shows the vast spread of different areas of technology that we touch. So that's about it really for tonight. I won't hold you up from your buffet anymore. I could do with some myself. I'm leaving a copy of the pack with the branch here, so you'd be welcome to get a copy from. Tells you how to contact us. We've got a website, ati.org.uk, fairly easy to remember. Just type in ATI into Google, and we'll be one of the top ones that Google hits. We Twitter about things. I'm not of the Twitter generation, so I don't Twitter very much. I probably do more LinkedIn. That's a bit more easy to understand for me. But we have a go. If you go onto our website, you can sign up to our newsletter. Encourage you to do that. Tells you what we're up to. So please do that. And you can download a lot of material from our website, all those insight papers, our strategy document, where it tells you a lot more about the sort of stuff I've been talking about. So I'll just leave you with a future vision, showing what the airspace might look like in the future with, yes, large conventional looking aircraft, some more advanced looking, highly fuel efficient, but also lots of smaller aircraft flying around at lower altitudes, probably electrically powered. Thanks very much.